Okay, let's get started. Of course, there's only four of us this morning, so in the second period, we might want to consider transforming these lectures to just recordings if necessary. But let's have a vote on that on the course website, because why not? Okay, anyway. This morning we don't have the backup audio capturing device, so the only microphone I have is that one on that laptop, so I'll have to try to be mostly staying here and yell at the microphone because it's a crappy one and I really need to be speaking towards it so that it even captures anything. But anyway, today's topic actually is quite huge. It's about software maintenance, surprisingly, like always, but it's also several smaller things. It's more about terminology to understand how and why we assess the existing source code or the existing project or do things in software maintenance, and also about things that you probably have already heard at least once in software development, but in software development you don't have any reason to do those things. So you might know the terms, but you don't have an idea on what they actually are. And these things, of course, are the code smell and these sort of refactoring things, rewriting code, and these sort of approaches in the software maintenance. But as always, let's start with a quick recap from the last week. We were talking about regression testing and live development models. So, like I mentioned, the regression testing is done to check that the system still works after some changes are done to the behavior or the structure or architecture or whatever things we have to change or add or adapt for new technology or for new customers. Of course, the problem with the regression testing is that usually we don't want to test the entire set and the entire software, the entire ecosystem, the entire infrastructure, because that takes just time. But the idea is that we try to find the things that affect the parts we fixed or changed, and we test those and see that they still work within the new infrastructure. This is also a topic we will be expanding today. But anyway, in any case, the problem with these, regardless of the approaches we use, is that we usually inject bad fixes, bad patches, bad things, new broken features to our software, or just cause a bloat to our software or system. We lose performance, we lose actions, we lose some support for the low-end resource-based systems. These sort of things tend to happen. For example, on several occasions, the low-end internet connections are just no longer supported because, well, the new system is so bloated that it actually needs the bandwidth. But on the other hand, the infrastructure has come to the point where these sort of very low speed broadband connections are no longer used for customer service. Also, well, you probably have noticed that some mobile phones tend to become slower over time when you install new and new patches, and it just keeps bloating the software to the point where it might actually stop working. So these things are more or less side effects of adding features or fixing things that were found, and are sort of bad fixes in a sense that even if they don't actually break anything, the worst kind of bad fix is something that just adds new broken things. The bad fixes also can be something that hinders the entire system. And to counter these sort of broken or bad fixes, we have to revise and fix the system itself. But we'll get back to that on a couple of slides. Anyway, we also talked about these things, how we start with the daily build and smoke tests, about software integration, to start with extreme programming, continuous integration, and continuous deployment, delivery, and so on and so on. Giving you a sort of an idea that even though we are talking about rather new aspects or new approach to software engineering, considering that the agile things weren't really thing when I was, for example, taking these courses. These are the modern ways of developing software, because we have to be able to react to the customer needs, requests, shifts on the market interests, or new requirements, or new architectures, or new technology in a quite rapid degree, because the customers no longer are comfortable waiting for 1 year or a couple of months even for better support for new device. If a mobile developer pushes out new mobile phone version or something like that, so software applications have to update and be compatible with that version of the system immediately, not within 5-6 weeks, months like earlier. So we have to make something or define something that supports this type of rapid deployment or rapid development to keep our software or system available and customers using it. So the continuous delivery, continuous deployment, these approaches are trying to address these issues. But even if they are rather new as software engineering process models, they are more or less successful implementations of things like extreme programming or the daily build approach, which are now pushing 25 years. So nothing is really new, but on the other hand, these approaches are successful now because we have the infrastructure, we have the tools to actually support these sort of activities, even though we already earlier knew that these things could be done, but they were unnecessary or unnecessarily costly or something else which hindered them. Finally, like in everything, the problems are connected. So the product design may cause problems with the build design, may cause problems with the integration, which by itself is full of problems with everything, and the testing work tries to assess that the product design, integration, these sort of things are actually done correctly, that the system does what it's supposed to do and the system works correctly. So on this aspect, we come to this week's topic, which are code smell, refactoring, and technical debt. These things are more or less a symptom of doing revisions or patching code or making fixes or adding features or making things quickly, cheaply, by cutting corners, by competing up against other people, and also sometimes simply because the system is old. It has been available for a while, it has been on maintenance cycle or support cycle for a couple of years. It has migrated from the original platform to somewhere else, and it's not always possible or worthwhile to do a very good job when it's enough to just see that everything works as expected. So in a sense, these things aren't absolutely negative things. They exist in all projects. They just have negative connotations because usually they all mean that if you have to do some of these, then your product has a problem or it isn't of as high quality as it could be or should be. but still keep in mind that these things always exist in all types of projects. So let's start to see what these things actually are. Well, first of all, what happens when the software gets old? This is a slide you saw earlier, and this is the list of things or indicators which define that there's a decay in your system. You are facing problems because you have been maintaining or updating or patching your product or your system for a long time. There has been changes in the personnel, there has been relaxed documentation standards, or you are in a situation where you have to just release a fix to some major problem after problem after problem after problem, and your documentation doesn't stay updated, or your customers simply require you to do rapid development cycles and you don't have the resources to keep everything up to date. Also, you don't even have to have a process problem, really, to have this sort of situations. For example, the very large components and they're running in emulation mode are simply technical things. You don't, the product doesn't pay enough to do a full native port to a new technology or platform, or that there has been need to add features or add support for compatibility, these sort of things, which means that finally the parts of your system which manage, for example, hardware communications have become quite complicated and difficult simply because they have to support so many different hardware options. For example, with the operating systems, there's really simple example here. The most simplest form of Unix kernel, which just boots up. It doesn't do anything interesting, it just boots up, loads the disk, allows you to manipulate the disk contents and these sort of things. It expects to be an x64 processor architecture. It's less than 10,000 lines of code. And that's basically an operating system. For another example, Windows 3.1, which probably is something that all of us here agree is a sort of a modernish operating system, graphical user interface. It allows us to add tools and plugins and stuff like that to use, for example, a web browser and stuff like that. It has about 2 million lines of code. It was written by 200 people on a time when basically all the home PCs or systems were IBM PC or something that was a clone of an IBM PC. So 2 million lines of code. Whereas if you take current operating system, whether it's Linux or Windows, it really doesn't matter here. It's more than 100 million lines of code, simply because it has to cater so many different variations, options, activities, these sort of things. So from less than 10,000 lines of code to more than 100 million. And basically what we have is a software that's more or less doing the same things. The other ones look fancier. They have more abilities. But of course, they have become a huge thing. So in this sense, you have to remember that it's not always a negative type of bloat things. Of course, I know that, for example, Windows Vista was a complete abortion of our operating system because it was slow. It didn't really run well anywhere. The security features were mostly annoyance features for the users, but the security on the technical side still didn't work properly and these sort of things. So that was a legitimate bad product. But for example, if we take into account what type of operating system we want, or is it one hardware or several different variations, we end up with with complex structures and large components by themselves. We don't even have to do a bad product and we still have these problems. Anyway, of course, we can improve after we have launched our product. On this course, we always expect that there is an existing code base somewhere on which we are doing things. Of course, one of these approaches of what sort of maintenance we do is preventative actions, which means that we try to enhance the maintainability of the software. Of course, because the West side won the Cold War, we are not in a socialistic utopia. The preventative actions aren't very well liked because they usually don't generate money. They don't add features, they don't add new users, they don't add things. They just make future easier. So they are only 4% of, well, they are assessed to be 4% of the different types of maintenance projects done on software, but still it's a thing. You have to do that at least when you are making the new ported or added support for new architecture or software or system. You have to do something to this degree to actually be able to support the new hardware. Anyway, if we are doing preventative maintenance, it means that we are trying to fix problems, or we are trying to make things simplified or easier to understand, easier to read, get rid of duplicate things, get rid of legacy stuff that no longer works or is no longer necessary because it just keeps adding unnecessary complication to the source code. So on this aspect, there's these three things: code smell, code refactoring, and technical debt. And on this lecture, well, rest of it at least, we are going to go through all these three things, what they mean, give you a couple of examples of what these things might be in your project, how you can assess or what sort of clues you should look for to understand that, okay, I might have to actually do rewrite this part and refactor that code and these sort of things. So let's start with the technical debt, because that's more or less the starting point. We take technical debt to, or we cause technical debt to appear on our project, and we can because we expect that we just make something work now and fix it later. It's not more complicated concept than that. It's all the cut corners, all the rubber bands and band-aids we use to keep the source code together, and that's just the terminology for it. So basically, there's a number of definitions here. Of course, these are taken from different textbooks and other presentations. They aren't, well, that they are unnecessarily complicated in some cases, but well, it's basically technical debt is delayed technical work. So instead of using coding conventions or making robust test scenarios or unit tests or test automation or ensuring that all the weird or extreme cases actually work as they are expected to be work, we just cut corners, take shortcuts during the development, and have been actually also taking the shortcuts on the previous maintenance cycles. Basically, it also means that we don't do work that prepares for the future. We just do things to ensure that today or tomorrow or by the deadline, our system builds, boots up, and does what it's expected to do for acceptable number of users, like 99% of users. The 1% who is using something weird or doing something weird with our software or service can wait for the extra patches or something else to help them. So basically, like I mentioned, the technical debt isn't actually something that should always be avoided, because we live in a world which is realistic, and we have the resources, whether it's people, money, or time, to do things. We always have to take some technical debt on our projects. So basically, it can come from basically anywhere. It's a design that was put forward before we actually consulted all the users, or we use simplified technology or simplified techniques to implement the architecture just to get things working, or we have to release our product to our customers so that our studio exists 2 years from now so that we can make the other things we would like to have. But we have to put something out now to stay in the market or have customers or users or something like that. Or as simply as some actual game studios I've been involved with actually keep saying that the last category, the prudent inadvertent, is actually quite usual. We have now more experienced people. We know what our customers expect. We know what we can do with our tools. Overall, our organization is now much more confident and capable of actually developing something. So the product might be or would be much better if it was written today, not 2, 3, 4 years ago. So also the lack of experience is also something that might cause technical debt, simply because the team which made the product originally didn't actually understand the long-term consequences of their design or implementation choices. The graph on the right side is well, it's really not very it tries to imply the same idea, but the idea here is that remember that it might be your experience, the prudent inadvertent. The prudent deliberate means that we are just releasing something, or we don't know how the system should have been done, or we don't have resources to do things properly. So all these things, they happen in all projects, and they are technical debt, things that are left in the product which need to be fixed later. So what usually is considered technical debt, or what happens when you are using the rubber band sort of thing, spaghetti code approach, means that your software process itself tends to drive towards more problematic things. Of course, I'm not saying that it's impossible to run commercially successful project while having a horrible code base. I actually know people who are doing this and they are doing just fine. But in general, if the product has huge technical debt, you might have things like you are spending most time trying to fix bugs, or trying to find all the different things which are broken, because something that's simple to fix, or should be simple to fix, isn't actually simple when you are trying to do it. It costs more, of course, because you have higher man hours, you have problems, you have resonate problems. For example, something happens because things weren't thought through, or the customer don't like your product because it's slower than your competition, it has less features than your competition, it's unable to respond to the changing needs of your customers. This is actually something that ended up killing, for example, the Microsoft Lumia or Nokia Lumia phone line, because it was mishandled to the degree that there were people who were trainees trying to do stuff that the competing companies were doing professionally. You finally ended up with a situation where you had long delivery times, poor customer responsiveness, and finally the entire ecosystem was just dropped because it couldn't compete anymore. So adding technical debt on technical debt finally causes the organization to lose the competition to other things. In open source environment where you might consider that you don't have competition. That's usually the point when there's going to be a branching project or cloned project. For example, something simple like OpenOffice. You all know how well that went when the organization decided that they don't want to do user interface overhauls, or they don't care what the users are saying about the system. They are just trying to add new things, or I think it was scripting language inside the OpenOffice. So now it's like 5-6 different projects, simply because it had all these problems and no one was willing to actually start to fixing them. Anyway, the problem, this means that from the maintenance point of view, that the cycles are laborious and costly. It costs more, it takes more time, people are frustrated, want to quit, change to another organization, these sort of things. So of course it's going to be a major pain in the butt if you are trying to run your business. So if we are looking into the source code or how the project is managed, these sort of things you can measure. These sort of things you can see and are usually a very good telltale signs that there's, or evidence that there's things that should be done differently. So there's a huge amount of duplicate code in your system. You don't comply to your own rules. There's really lack of comments, or there's too much comments here and there, because actually surprisingly, when people don't understand what they are doing, or they are uncertain that something works, they also have a habit of leaving comments behind. It's actually eerie how well that thing, the amount of extra comments and the brokenness of that same code actually correlates. Or something's just deleted because it was changed by someone who didn't bother doing the other changes. There's interdependencies on the package, meaning that the cohesion is low, and that's or that the things need each other. They are not developed or maintained in a degree that it would be simple to keep the objects working. There's unnecessary complexity, and also the test coverage, whether it's automated or manual, is poor. Usually the low automated test coverage means that, okay, the system isn't maintained or kept up to date as much as it should be. On the other hand, some organizations simply don't do automated testing. It's a bit weird, but still someone do it. And also the amount of manual testing you have to do to actually release something. That's also a good metric. But in general, trying to battle the depth or trying to improve the maintainability of your software usually means that you try to fix these things or put them as they should be, starting from here and going downwards on the list. Because if we just make more automated test cases, it probably is just waste of time, because, for example, the amount of duplicate code means that there's something inherently broken in your system when it needs to have the same things explained in several places. For example, there's a design error or something like that, which makes the system necessarily to have the same thing on several places. Okay, so of course, we can't always blame the developers for technical debt, or that the developers are the root of evil because they don't have the skills to do the wonderful things we as a software developers or software designers give to them. Of course, they are just implementing things. They are making the features, implementing the things that are designed or which are the consensus of the current situation. If we consider the entire software organization, usually these sort of things listed here are the root cause of miscommunication or situations where we don't simply have the knowledge necessarily to do a good job. So of course, the poor coding and testing practices are pretty self-explanatory, but still something like system design, communication and collaboration between different people, for example, are one very fine and simple way of making horrible software. It doesn't matter if you have 30 professional people who are headhunted from the other companies making your software. If your lead designer and the project manager or lead designer and the marketing director don't want to talk to each other because they hate each other. It's actually stupidly small things which might cause situation where your company or product simply isn't doing what you want, what it would need to do. Also, there's no standard development process. It doesn't mean here that you have to use some IEEE or IEC standardization or these sort of things. Of course not. It means that you should have some way of doing things in your organization. Just one default way so that everyone in the organization knows what should be done now, what should we do when we design things, where should I put the results, where should I take my next assignment, who is doing what, these sort of things. Of course, not really a rocket science, like I've been trying to say here for the last 4 weeks. Also, no definition of done, no requirements, no definition of what we actually want the system to do. Like I mentioned a couple of weeks ago, there's no inherent good quality, there's no inherent idea of that everyone has on what they want the product to be. So that has to be defined so that everyone actually knows what should be done. And all these things, of course, cause the situations where people are doing duplicate work or adding duplicate modules for different activities simply because they don't know that the other parts exist. So, considering how this technical debt is battled, there's, well, the repayment plan here is a bit corny thing because we don't actually pay anything. We just try to fix the problems. So if we are doing normal maintenance cycles, it actually means more or less that we just try to pick out the most problematic modules, the most offending things in our system, and for one maintenance cycle, just fix those things. Of course, from the management point of view, that's going to be a huge problematic thing because you are just trying to get people out from the development work to do something that may not necessarily even be possible to do. You try to fix the module, you try to refactor it, you try to recreate the module so that it uses more simplified approach or divides the problem to more manageable chunks. And then what happens is that it's not possible to do. So you wasted one maintenance cycle. But on the other hand, if you have professional organization, you know that sometimes you have to do these things and also that not everything always works. But anyway, there's a couple of things that could be done, how to explain these things to the customers or your organization or people holding the purse, deciding on what we will do on the next iteration. So of course, the idea is that it impacts the responsiveness, cost, and delivery of the product. It also means that you need to fix these things so that you can actually, on the later life cycle, add more features or ensure that you don't have huge problems with the software. Also, it might be worthwhile to have a realistic plan because of course you will need to sometimes fix these things on every project. Like I said, this is a thing that happens over time. So especially when you go to software industry, you are the project owner or someone else making the decisions, you also might want to remember that these things need to be done. Even though that marketing people say that no, we don't need to do that. Just why are you writing bugs in your source code? That doesn't make sense. Well, that's not the stupidest thing I've heard. I mean, the president of the United States commented that the global warming isn't working because the polar circle is now in central USA, but it's really not even funny anymore to laugh at Donald Trump because it's just sad. Anyway, going from politics back to software engineering. The code smell and refactoring, of course, are the things where we are trying to find the problems, trying to identify the offending parts so that we can actually then pay back the technical debt. And the refactoring work is the phase where we are trying to do the actual fix itself. Yes. Mm. Yes, the question in the audience was that is there tools or what are the tools of assessing the technical debt? Well, usually, at least for the duplicate code or these sort of aspects, there are tools that highlight the parts which are too similar to each other. Also something like branch coverage analyzers for the automated testing is something that's fairly useful because it shows which parts of the source code are not visited even once during the automated testing, or what parts should be tested manually. And there's not really that much tool automation in a sense that there's not a one simple measurement which shows something from 0 to 100, and when it's over 75 it starts to whistle or something like that. There's a ways to measure different attributes like the branch coverage or the code coverage or the amount of duplicate code or the amount of comments against lines of code and these sort of things. And you have to make the decision that is this good enough or not. So you can the system can show you the parts where it considers that, okay, this might be broken or this might need some attention, but there's no smart tools enough to explicitly say that that line or that module fix that. That's what your professional capabilities come in. So, but anyway, on the code smell and refactoring. So, of course, this starts from the same premise than the technical depth. So we know that good developers make bad software. We also know that requirements change over time. We know that it might be hard to keep up with the maintenance cycle. Might be difficult to keep the system relevant or able to run on the new hardware platform or keep up with the operating system after operating system and the operating system. And of course, at some point, you are no longer really making money by releasing the new version. You are just making some money by keeping your existing customers. So you might not have time or money to do things. But on the other hand, usually, if you are in a competent organization, you at some points are allowed to fix or recreate some modules so that they correspond to the current state of the system, because the original design couldn't really know what sort of things will happen in the future. The analog here is that, like painting a room or painting a building, it's always that your second work is always better than the first one, simply because you know more about painting buildings at that point. So similar analog here applies also to the software development. So there's actually two things. How do we fix our software? Or how do we know that our software is bad when it actually even still keeps working? So like I said earlier, you don't necessarily always have broken software. You just have something that's completely nightmare to maintain or complete nightmare to add new features. But the current iteration still works. So why should we do anything to it? Well, of course, it works now, but 1 year from now, it might not work, or it's outdated or outclassed by its competition. So in a commercial project, you are you are in hot water because why did you allow our product to decay to this point? Also, of course, when we are looking into a product which keeps working, how do we fix that? How do we know what to fix in that software? Of course, I mentioned the metrics, but of course, is that always the correct information? Well, let's consider into different things that we might have. First of all, well, the refactoring software code is fairly simple thing to do. It's it's writing the code or as it should have been done at the first time, or modifying it to improve readability, maintainability, extensibility, adaptability, support for new approaches, or ability to support new platforms and different approaches. So in the software itself doesn't basically do anything differently. It keeps doing the same things. It takes the same inputs and it sends out the same outputs. The other parts around the software doesn't even actually know that there has been some changes inside the one module. It's more or less similar thing as changing an engine on a car. Unless you own the car or owned the car or used to know what it was like, you're the only one who is going to notice that, okay, now something is different. But the idea is that we don't actually at this point or in the refactoring phase do any changes to how it behaves. We just improve or streamline how it works internally. So basically, we do not want to add new functionalities. This is one of the only things that almost all these new age extreme programming, agile development messiahs agree on. We need to have refactoring work done, but you should never try to introduce new functionality at the same time, because the goal is to make the code easier to maintain, easier to read, easier to understand, or more streamlined in a sense that for the complexity stays as low as it's needed to stay. For example, from the metrics lecture, we were talking about the cyclomatic complexity number. If the module has the cyclomatic complexity of more than 10, then the module is probably too complicated or prone to do errors simply because the developers might use it wrong. They might not understand all the different possibilities of what should actually be done. So also to reduce complexity, that sort of thing should be split in half. These sort of things are done, for example, in the refactoring phase. Of course, how it's implemented in a way that we put one overly complicated module to two parts and then keep the input and output still the same or the interface the same, it's up to the experience and capabilities of the developer. But still, it should be something that's done. And in the long run, when we have these to keep the interface same everywhere fixes, then at some point we might also want to simplify the interface itself, but that's a different refactoring cycle. Anyway, the idea is to make the source code more simple or less complex. So, of course, we know that when you do changes, anything really, to software, you will at some point make faulty fix. And of course, the refactoring can introduce problems, also because you made modifications to software, but also because you changed something in the internal works of the software. You might have actually done something that you didn't know or couldn't know because the software is a faulty piece of crap and removed something that was somehow used by something else. So of course, you can't also rely on the fact that, okay, I just remove the old module and put this new one in, because there's no inherent shape or rules regarding software modules. You also have to test that everything still works. This is also why management doesn't really like these things, because it's added risk, it's expensive thing to do, but it doesn't actually do anything in a sense that it's not new feature. Also, it means that you have to retest everything to ensure that things still work. In regression testing, you just check that everything still keeps working because you just made a small modification to an existing a module, not changing the entire thing. But if you are doing larger refactoring work, you might have to actually do all the tests and do all the quality assurance steps to see that everything works, at least if you are doing something radical or large-scale changes. So there's a couple of quoted lines here added by different people doing the live development process models. These same names, Highsmith, Beck, other people keep repeating on all the slide sets simply because they more or less are the people of software maintenance or live development approaches. So, for example, Highsmith says that the refactoring is one of the most important technical factors in agility. Highsmith also said something like after every 10 or couple of cycles, you should refactor all the central modules because you have made so many small changes that you will start to have to accumulate technical depth unless you refactor everything you just did. Also, there's the idea that the duplication and needless complexity should be removed every time when you make some changes, or doing this, creating testing for the test cases or test automation for extreme programming approaches. I think especially in extreme programming, the idea is that each addition of feature or each addition or revision of anything you do in the software is basically a rewrite, complete revision of the module, meaning that you are constantly doing these sort of activities, getting rid of needless complexity and getting rid of needless duplication of things. Of course, this is a nice idea, but it's really laborious thing to do. And Beck's definition, we do changes that leaves the behavior unchanged, but the non-functional qualities, simplicity, flexibility, understandability, performance are enhanced. This is more or less something that most people understand how what the objective of the work is. It's about the understandability, because we all know that we always lose developer or lose people in projects at some point. People decide to change jobs, go to cross country somewhere else, get married, move away, have children, drive under a bus or something like that. So we always need to keep the system understandable or documented, preferably both, but still. The idea is that these actions aim towards making the entire system more or less self-documenting, even though the self-documenting source code is a sort of a joke, at least in software engineering, because that's only one reason why people don't want to write the design documentation. Also, well, Fowler's definition follows more or less the same idea. The Martin brings out the economy aspect. It should be cheaper to revise source code that's already simplified. It's also easier to add new features, and that's also something that should be kept in mind. And finally, making a sort of list of all these things. So it promises million nice looking things. Remove duplication, enhance software quality, make the code more flexible, easier to change, so on and so on, save the pandas and these sort of things. But the idea is that even though this is more or less a list of propaganda, more or less, the idea is that, of course, if we want to improve software maintainability, we have to do these sort of things to ensure that it's actually easier or even possible to do our job properly. So why refactor things? Well, there's a list of things. Well, we also find bugs. We find things that are badly designed. We increase readability, reduce debugging time, so on and so on. So there's really several reasons why to do it, especially if you have downtime. You are, for some reason, we are not developing new feature, or we are not in a hurry to do something, or we are just seeing how the system performs with the customers. You might want to refactor some more broken parts simply to get the clean the messes up, so that in the future when you have to do things, or some of the things are already done. Also, well, you should also start, of course, from the code that smells, which means that the problematic parts. On an earlier lecture, it was mentioned that 80% of the problems are caused by 20% of the modules. These are also the modules that cause or generate smell, meaning that there's something wrong with them. They are there's some things or some measurement or metric which can be used to say that this module isn't as good as it should be, and this one is something that should be refactored. Basically, the idea is that, well, you start with something that works. This is important. You start with something that works so that you don't spend your time fixing those bugs, or you have a code base which ensures you that now you are done, now the fix works. So determine what you want to do and ensure that after your work, everything still works. This is important because this also ensures that you don't introduce new bugs or broken patches or bad fixes to your system. And like I said earlier, one of the only things that these agile evangelists agree on is that you should never do simplification work or rewrite work or anything like that unless you have a build that actually works, because that's the baseline for your work, to understand that when your work has been enough. So, well, there's some things that Beck, for example, says that that help or are required for refactoring to actually work as a tactic. Of course, these are from his own ideas, and for example, that the Beck says that you have to do continuous integration, which, by the way, is his approach for software engineering. It's not really surprising, but the idea is that you should have some things like coding standards, so you can identify the parts or know how things should be done. you should have people who actually care, if that's possible to do. Rested programmers here mean that the people should be willing to do these sort of things. It's a bad idea to try to fix things which aren't broken in a case that your own developers don't understand why you are doing this, because it quickly devolves into an army style of manual labor of doing things because we are saying that you should be doing things. So this week we are digging a hole and next week we are filling the hole because we have nothing else to do. That's a bad management style, so keep that out. And also be ready to do it anywhere you need to. So you might want to refactor test cases. You might want to consider test automation, user interface, whatever customer considers that could be better. So in a sense, there should be no holy cows or something like that that you won't touch. If it needs improvement, that should be okay. If you run into a problem that you can't fix something, it's also an alarm or red flag saying that there's something else problematic with that software. Of course, if we are in a huge, large international corporation, we don't always necessarily know all the details behind all the decisions, and we all only might get only one part of the system for our team to develop or perfect. But still, refactoring should happen every time we find something or some source code that smells, or i.e. it has some features which are problematic. So these ideas on when to refactor all the time, well, that's the simple answer. Also, the candidates for things are when you add functionality, when you learn something about the code, meaning that you learn something that shouldn't be, or when you fix a bug from something. You might want to also consider the simplification step, that after the functionality works, or after the bug fix works, or after you have confirmed that, okay, hey, there's some design issue here. After you have confirmed that what you did earlier works, then you might also want to refactor that problematic aspect away. And in general, the last thing of this lecture, the code smell. If you don't have any of these, then you can start looking for the problematic areas, which means that you start to look for code that smells. Okay, so finally, well, if the tests don't pass, then you should focus on fixing the build, then start doing that work. But that's already something that we were talking about. So don't do this as a last thing before deadline or delivery. I have actually also seen this in real life. It's really nice to. I heard it's really nice to travel to France to have a meeting in Paris with your potential publisher, and your developers had managed to break down the build last night. So when you go there, upload the system and try to show something that works, nothing is happening because some jackass decided to start fixing the physics engine bugs the night before. So don't do that. Don't be that guy. Be the guy who fixes only things when they are passing. So, of course, it's also tinkering if you do it too much, and you might not also want to do these things to databases. So, and if you have huge amount of customers, you might want to run the changed user interface through some designers or people doing marketing research to see that your upgrades actually are upgrades, not unnecessary tinkering work. Because of course, as an engineers, we like to perfect things, but on the other hand, one of the most horrible things the engineers have ever devised were the remote control for VCR cassette player, where they managed to scram into VHS player remote control more buttons than are in the typical PC keyboard. I still don't understand why that remote control needed to have over 300 different buttons with Shift and Alt keys combined. But hey, some designer or some engineer in some, I think it was Sony factory in 80s, decided that this is a really cool thing to have. Well, it wasn't, but still. So, meaning that of course this can also be a sickness if you overdo the work. So if you agree on some stable build, then that's probably also okay. This is not a religion, this is just decisions. So, of course, there's aspects if you go into real life, there's lack of understanding, there's no pay, they are not paid to do refactoring work, or there's no financial interest in it. So don't be surprised when you are told that these are things that we are not going to do. Also, the one thing is that the breaking the current program or breaking the system is really huge problem. The downtime in each service or application is something that just costs money. So of course, try to understand that when you are working in a real life project. So going into the last part. So what is the code smell? So in general, it's an indicator that something is wrong with the code. It's not very concrete thing. It's just things that could be different or should be different. But also there's also false flags in the sense that sometimes the code might look it's broken, but it's actually not too badly broken. But the slides I'm showing you, just some of them here, are from the book Refactoring Test Code, which more or less lists the different design patterns or anti-patterns of things that indicate to you that the code might be broken. So you might want to take a look into that book, because for some interesting reason, I'm not going to be here in front reading you out loud the entire book from cover to cover. When you need these sort of things, get that book and look from there. But the idea of what are the different types of things that indicate that the code is problematic or there's a smell in it, there's several things there. These all are taken from that book. We'll take a look into a couple of these things. There's some funny like shotgun surgery, or some lazy glass, or something really not funny like inappropriate intimacy, which means that the objects don't follow their visibility rules, or the library class which doesn't actually work, or these sort of things which are really freaking annoying problems if you have to fix them. But still, of course, if you find one of these, you know, at least you know that I found a huge problem in the design or architecture of our software. So other things, lazy testing for testers only. So there's a huge built infrastructure within infrastructure for testing work only, which might or might not be up to date, and which might or might not cause some weirdness to happen when the customer does something unexpected. So yeah, a really large amount of different things that could be problematic. So in general, the commenting actually, like mentioned, is also one of the easy ways to see where the problems probably are. This used as a deodorant for other smells is, well, again, simplification. Of course, you need to have comments. Of course, you need to have the decoding conventions, or explain what are the inputs and outputs and what the algorithm actually does. But actually, like I mentioned earlier, it might indicate that this is a code or block or area which was difficult for the developer to understand what it actually does. It's alarming how well the extra comments and the amount of problems in some source code correlates. And this isn't even a joke. There's actually been studies on this aspect, at least for the last 10 years when the rapid deployment and these sort of things became a thing. But usually, because the comments are also used by the developers to explain to themselves what they are trying to achieve, it's actually a very good way of finding areas which were problematic or complicated or difficult to wrap your head around. So it might also be prone to errors as a thing that was implemented. So of course, there's simple things, duplicate code. So if the code repeats in multiple places, you can do different things like take the method out, take the class out, add the method to somewhere else, or make it responsibility of someone else, or use a template method if your programming language or infrastructure allows that. Also, something like a class which only exists to hold data has variables, getters, setters, these sort of things, which might on some occasions have something to do, but still it might be actually easier or more useful to just encapsulate all these things and send them as a data to different places. Data clumps, set of variables, pass it together, make them as a list or tuple or whatever datagram array things to ensure that they actually go together if they are expected to go together, these sort of things. Classes that use too many things that should be private in other classes, so there's problems with the visibility, or some object is designed so that it actually relies on things that it shouldn't even have access to. Large classes. Okay, so it's too complicated, it's too complex, it's trying to do too many things at the same time, it has much variance in it, it has too many paths to take from input to output, so it should probably be two or several other smaller things. Lazy class, it's just there because someone designed it and then they found out there's nothing to do with it. So just get rid of it, put it in a chopping block, and so on and so on. So basically, these different ways of identifying what's problematic or what are the problematic areas, or what are the modules or components or objects, depending on your infrastructure, which might need revision or doing rewrite work, are actually quite many. Well, some of them might even be actually problematic because they just add complexity and might cause problematic behavior. Of course, there's a couple of ways to fix the smelling code. You should probably analyze and determine if you want to fix this or not. Some purists say that get rid of everything. If it fulfills any of the criteria, just refactor it. But of course, since we live in a reality, you might also want to consider, is this really necessary? If it still works, or if it's something that affects too many places at the same time, or is it just complex because it needs to be complex, then you really probably shouldn't be tinkering with that. And of course, like I mentioned earlier, the list of things that might be broken, the list of things that might say that, okay, this code smells, there's technical depth in this part of the software, we need to revise this module. The list is huge. It explains these things on well from the object-oriented programming point of view. And there's complete books, like mentioned earlier, so you are better off if you go online and check for those patterns and anti-patterns of object-oriented design, what sort of things are maintainable, what sort of things are not, because there's over 30 of them. basic models and their applications on different programming platforms and programming languages. It's not worthwhile to go through this list here, similarly as it wasn't feasible to go through all the different quality metrics on the different standardizations. Also, of course, keep in mind that your source code might not be the only place which smells. There's several things, for example, the test cases, automated and manual, and also on the libraries you use. Mostly saying that if you are using library, which doesn't actually do all the things it's expected to do, then you shouldn't probably be using that. But still, there's things for test methods like duplicated naming information, causing problems, or eager testing. It just keeps calling different objects. It doesn't really focus on anything. Or like I mentioned earlier, there's a huge amount of production code which is only useful or used by the testing phase. So it might not be isolated well enough that it might cause erratic behavior or something stupid like variances on the user experience or something like that. One of my favorite things, for example, or examples here, is that the I don't remember what the name of the game was, but the insects which were invisible and not available for the player to see were left in the code to test out that the 3D physics and other things work. So the place looked like haunted because all the chairs and stuff move here and there because the developers forgot that they have a debugging small AI insects running around which they were using to test different paths and these sort of things. So of course, in a game might be okay, emergent behavior, stuff like that. There's invisible ants in this warehouse, be aware. But if we are doing something serious, that's going to be a huge fucking pain to ask to find why this thing isn't working as it should be. Also, libraries which don't provide all the needed methods. You have to fix the library before you can use the library. You probably want to switch out from that. Or if it provides erratic updates, versions which are incompatible backwards, like for example several things in Ruby likes to do, then you might want to consider that this might not be the thing that I want to use in my commercial product. Some design aspects, primitive obsession, using primitive data types when something more advanced would work, but because it's more advanced, we don't want to use it because everything has to be a list of pointers or list of pointers pointing to matrix of pointers. Those people who know who I'm talking about, well, have a nice day. But still, these sort of things can be a problem because it also adds unnecessary complexity to your solution. Resource optimism. We expect that it's always available, these sort of things. Really annoying problem with the testing features because if it's not available, then it's a false flag or false positive error caused by the test case itself, not by the software. And then you spend an afternoon trying to find out why this test case fails. Well, these things go on and on and on. So basically, all these things are problems, obviously. Good thing is that there's also things like lists of explaining what you should probably do to them, get rid of these problems and how to fix them permanently so that they don't come back and haunt you when you are trying to do the next major revision. Test code duplication. Well, yeah, similarly as any other duplication, unnecessarily typos in your software code. But anyway, important thing here to remember is There's wealth of these things. Of course, there's also different opinions on many of those things. Is it really a problem or not? Like before, because software architecture isn't building architecture. We can design whatever we come up with buildings. Things collapse if we don't use a good enough foundation and these sort of things. But still, the idea is that there's several things which we can observe, for example, from object-oriented design, or by making an analysis work on how the structure is built. Is there unnecessary things? Is there something that we don't really need? Is there legacy stuff, which usually is the source of some of these revision needs for the modules? And finally, of course, even though the source code itself is the famous source of smell, it might not always be that the problem, that the area which is broken. Because bad test sets, bad test automation, unmaintained documentation, bad architecture, weak software process, undefined requirements, bad solutions in general are all causing the same problems. They cause us technical debt, they cause the project to cut corners, they cause implementation errors or miscommunications, which mean that different things don't behave like they should be. And finally, we end up doing analysis on the source code, simply because that's where more or less every process error or every shortcut or every wrong thing that was done wrong is codified. But usually it starts with the architecture, it starts with the design, and it's also reinforced by the bad practices and processes. So what's to remember from this lecture? Well, not these things, because I think this is from the first lecture or somewhere. What are the code smell? What are the technical depth? What are the things we talked about today? How do they relate to each other and software maintenance? How, for example, can we observe what needs to be fixed, or what could be fixed, or what could be improved? Also, the flip side of the coin, how can we assess that if this is something that really needs to be fixed, or is it broken enough? Or how can we measure, for example, that does this code have enough problems, or is this overly complicated, so that we should do software maintenance cycle where we fix these things? Because in real life, software maintenance costs money, so we need to first know what we need to fix, why we need to fix it, and how could we fix it if it was approved or decided that, okay, today or this week we are improving our software maintainability. And that's that. 1 hour and almost 20 minutes, like previous weeks. So not exactly a short lecture, but still we ended before the clock ran out of time. Anyway, thank you for this week, and I'll just end this recording and then we can have more questions.